Welcome back everyone. I hope you guys had a nice lunch. So next up we have Professor R. Ramanujam. He has been in faculty at the Institute of Mathematical Sciences for over 30 years and is now a visiting faculty at Azim Premji University. His research interests primarily lie in logic, concurrency, game theory, etc. And he has also been deeply involved in science education popularization. He has done a lot of work in this field, and it was recently recognized when he was awarded the Indira Gandhi Prize for Science Popularization by Indian National Science Academy in 2020. And today he's going to give us an introduction to algorithmic metatheorems. So join me in welcoming Professor Ramanujam.
Thanks. Can you hear me? Is it on?
Yes.
I'm not getting much feedback. It's okay. Fine. Oh, yeah, so thanks very much. Thanks. I thank Aditya and other organizers. Statutory warning is that my work is mainly in decidability theory, and but I've been learning descriptive complexity of graphs and teaching it as well, so it's going to be related to that. And do feel free to interrupt me. Okay, so the title was Logic for Algorithms. So what do you know of logic? Anyone? First order logic. Okay. Anything else? What is it about?
It's basically how we formalize our intuition.
Logic is formalizing intuition.
You want to remove human thinking and make it purely mathematical.
Make it inhuman. Yeah.
No, yeah.
Any other? Okay, so in fact that takes me to the next question. Do you think logic is useful for making it inhuman? Any other use for logic? Aditya, you think it's useful? Completely useless. See, this is what, I mean, if you are a PhD student in theoretical computer science and IISc, you should be saying that, right? Yeah, what about my colleagues?
I think logic forms the basis somewhat of what we are doing right now. Like we can't do all that without logic. We need to.
But somewhere so deep that
Yeah, it's like
who cares
secondary.
really, right? Come on.
Yeah, like all the models that we work on are basically logic. So if we remove logic, we don't have models.
Yeah, but then logic becomes everything, and then that's not particularly interesting, no?
No, it's
Okay, thanks. Thank you. But what about this? Yeah, here. Do you think logic is useful for theoretical computer science? Do you think logic is used for algorithms? Yeah? I don't know. This whole thing is an algorithms breakout, right? In this winter school. So is logic really useful for algorithms? I know many algorithm people will say it's actually a hindrance. Come on. So I don't know. So this is a question that I want to ask. Well, I don't know what you're going to think, but let me see. I'll try to convince you that it's of some use. Okay, what about here? So how many people have done a formal algorithms course? Okay. Some number have not. So what are the kind of algorithmic techniques that you know of, remember? Tell me a few. Divide and conquer, that was first round. Then dynamic programming. BD. Okay, then optimization, would you call that a heuristic? Okay. Approximation algorithms. Is that again? I mean, would you put approximation along with divide and conquer on the same platform?
Local search.
Google search. Yeah?
Local search.
Local search. Because Google search is a wonderful algorithm we all use every day. Right? Yeah, so that's a good algorithmic technique that I know of. But yeah, okay. Local search, branch and bound, go with the winners. There are many heuristics that you. But when you learn these things, at the end of which, what's your next question? I mean, I've learned some 5 techniques, 6 techniques, maybe 10. What's the 11th? What's the 12th? Who's going to come? I mean, Aditya is going to come with yet another bright new heuristic, and then I'll have to, the next semester students will start learning that. Come on, don't you get some uncomfortable feeling that you've got a whole bunch of, how does greedy relate to branch and bound? How does divide and conquer relate to dynamic programming? What's the relationship between the two? Did you get some uncomfortable feeling that kya yaar, I'm learning a whole lot of stuff. How do I even put them together? Did you ever feel that? Look at that lucky guy, right? So, okay, so I think I felt this when I was learning algorithms all along, that a lot of very interesting tricks, useful tricks, and I can see where they lead and I like them. But then how do they relate to each other? How do I put them together? Again, I'll leave you with these questions. I'm not going to answer. So now let's get to, this is a winter school on theoretical computer. What is theoretical computer science? I've never heard of theoretical mechanical engineering. There is theoretical physics I've heard of. Kya hota hai? Well, ask these guys because they organize the course. But what about, give me some theorems in theoretical computer science. Tell me one theorem. Huh? What is that? Gale-Shapley theorem? Those poor guys never knew they were computer scientists. But they got Turing Award, Nobel Prize. For what? In economics. Okay, fine. But they didn't get the Turing Award. Or did they? No. Anyway, so tell me some theorem.
Cook-Levin theorem.
Cook-Levin theorem, okay.
Exponential time hypothesis.
Exponential time hypothesis, would you call that a theorem?
Not theorem, hypothesis.
It's a hypothesis. What about, do you know any theorems on algorithms?
Sorting has a lower bound of n log n.
Okay, that's not a particular algorithm. Very good. But any theorem on algorithms as a class? What about, do you know of any algorithms involving logic? This clearly, there should be silence, right? Okay. So I am hoping to at least show you one theorem on algorithms involving logic, and this is the idea of an algorithmic metatheorem. That's the. So this was an industry that was inaugurated by Ron Fagan in his PhD thesis in 1973, and he proved this result. It's 74 because that was his PhD thesis and the publication was 74. So a problem is in class NP if and only if it has a description in existential second order logic. I call this a theorem on algorithms, not a theorem on one particular algorithm, because it says a whole class of algorithms, right? Well, not class of algorithms, a class of problems. But the very fact that you bunch problems and put them in a complexity class means that you have some particular algorithmic insight or lack of it very often. There are complexity theorists here, and I love to give galleys to complexity theorists. So, yeah, so there are So it combines something, and it says that if I want to know whether something is an NP or not, all I need to know is can you write it in some particular logic. So I do find it useful, right? I think it's a good use for logic, especially in relation to algorithms. And then Vardy and Nimmerman, actually independently but together also later, showed that a problem is in class P, but only if it has a description in first order logic, somebody mentioned that, plus something. What is that? Least fixed point. A least fixed point quantifier. You are used to quantifiers like for all x and there exists x. So you can also write a quantifier like least fixed point x or something, and that's something, some formula, something that you write in logic, but you can associate an operator with it, which has fixed points and it has least fixed points, and therefore you can talk about x satisfying that. So if you add something like that, then you get a class P. Over-ordered structures, I must say, and glossing over certain details, because only logicians fuss about these things. Generally people here, they don't know what the hell you're talking about.
Sir, we don't know what first order logic and second order logic is.
Don't worry, you will see. Right. I'm just telling you that it's possible to prove theorems of this kind. So this is really a long advertisement for logic, that's all. But you'll have to learn logic eventually. I can't do that. So the point is that the PNP question, for instance, has a logical formulation. It says, if you knew what existential second order logic was, it says that the moment you have a description in it, does it already have a description in first order logic? Which is 25. Then NP would be equals P. or you should be able to prove that there are properties definable in that logic but not in this logic, right? That's one way of showing P not equal to X. So then it becomes a completely internal question in logic, right? It's only about descriptions in logic, that's all you're saying, right? Descriptions in logic L1 or L2, right? So it's a kind of a logical insight into the PNP problem. That's what I mean. Since then, there have been many logical descriptions of complexity classes, and this area is broadly termed descriptive complexity theory. And I want to give a flavor of one such idea from here, and I'll try to motivate. But the point is that the moment you hear 73 and 74 and 80 and so on, what the hell is, why did these guys invite somebody to come and talk about something 44 years ago, right? Come on, we want to do the latest stuff, right? Well, here's the result from 2 months ago. This is MFCS 24 from October 24, and if you see the culprits, it's same kind of names. I mean, Carmosino, Fagan, Liverman, Collitis, Lexner, Sendupta, couple of young people and some old people together, and it says every Boolean function on n-bit inputs can be defined by a sentence in first order logic having about n log n quantifiers, and that is essentially tight, and this number reduces to log n when the Boolean function in question is sparse. So I'm saying that these connections are actually run all through in many contexts and discussions. And what is also interesting for me is that the proof proceeds by studying winning strategies in a class of two-player combinatorial games, which are called multi-structural games. And this connection between logic and algorithms and connection via games is something, this certain class of two-player games which logicians have used for quite some time and have proved of great use in understanding combinatorial structures as well. We won't see much of that today, but so in this talk, I want to discuss a particular type of algorithmic metatheorem. The general pattern is something like this. If the problem can be described in a certain logic and the input can be decomposed in a certain way, then there is a certain kind of algorithm for it. Okay. So it's a theorem on algorithms. It gives you a guarantee that you can find an algorithm in this class. Okay. A linear time algorithm, a polynomial time algorithm, log space algorithm. This is typically the sort of thing that you're looking for. And you want to say that, hey, it's really nice, no? If by just by looking at the input, right? If I can pre-process the input in some way, then if I can decompose the input in some way, then I know that I'm going to get a heuristic that will work in polynomial time. Isn't it nice, right? That's a very grand hope. Well, you may not be able to do this for any property. It says that if I can write down that property, whatever the property that I'm looking for, in some particular logic, right? Then there is some hope. This kind of theorem will tell you that you can get a decent algorithm. Or, of course, you may also try to prove lower bounds are always much higher. So there is a classic theorem of this kind, which is what I'll talk about today, but I also indicate other things. So for instance, it says if a problem can be described in monadic second order logic, whatever that is, and the input has tree width at most k, whatever that is, then there is a linear time algorithm for it. Okay? So if you happen to be looking for a graph property, right, I want to check this particular graph property. Courcelle says that if you can write that property in my logic, right, and if the graph happens to be tree decomposable, we'll see that also, and then you can get a linear time algorithm for it. So it's a kind of package, right? It's a sales package.
There is converse for something like this?
I don't know, towards the end. Okay.
Is it dependent on K also?
Well, so this is the fact that at most k meaning you are fixing k, right? So bounded tree width is what I want to say. So I don't want to, so it's like a parameter. We can think of tree width as a parameter in which. So for those who know parameterized complexity, many of these things that I'm saying would be parameterized in some sense. So, one problem, usual problem. I live in an apartment in a block of flats. Typically every flat has a Wi-Fi router and adjacent routers interfere, and you would like to link routers such that no adjacent routers interfere. Now, here this is something when you, ideally you could do that when you build flats these days, right? If everybody is going to get a Wi-Fi router, right? So you could actually say, oh, these places you put rotors. There are some optimal places that you can put and solve the problem. So actually I can take such problem and this one I can reduce to 3 colorability. You are just putting an edge saying I should have different rotors on an edge and then I can use the same thing. Okay, what do you know about the problem? 3 colorability. It's NP hard. Checking whether a graph is 3 colorable or not is it's NP complete, and unless P equals NP, we cannot solve it efficiently. But sometimes we can apply a technique like divide and conquer to 3 colorability. That sounds interesting, no? Hopefully. Okay. Let's try to do that. Okay, I'm not going to discuss this. Let me just go over to the board. Now, I think I'll have to turn this off, right? And make this go off. I hope you are trying to copy this graph because you're going to check if it's 3 colorable. So, yeah, so let me also give it some names because I'm going to need those names later. A, B, C, D. Now here is a graph that the moment I see that it looks somehow like a tree, I mean this is not quite a graph, not a serious graph, right? In what way is it not? Supposing I color this, let me take, yeah, supposing I color this red. What should I write? I'm sorry, I'm used to writing, so color blue. Then I have some subtree here, subtree there, and I can try to reuse colors within them, right? So for instance here, I can try, say green, and then I can reuse the other colors. Okay, now let me, okay, I've already got green here. Distribute right properly. Doesn't matter, any one of them, and one of them here. Then I get a B here. I think that should be. Yeah? Now, basically what I was trying to do was somehow realize that these three here, right? I can take this subtree here, yeah, and 3 color it. I can take each of these as subtrees and 3 color it somehow. Of course, these are not trees, right? This part is a little graph. So, can I chop up the graph into little pieces in such a way that I can impose an overall tree structure on the whole thing, right? If I can do that, maybe I can solve the problem. This is at the heart of this whole idea of tree decomposition of a graph. If your graph can be decomposed into a tree like this, then you can hope to solve the problem. This is the idea. There is a very nice game. You can also think of a game on this. Let me. So, have you heard of the cops and robbers game? Cops are trying to catch a robber. That's all, right? Okay, but they are all on the vertices of this graph. Okay, suppose there are two cops. Okay, and the game is like this. You start off with your cop somewhere and robber somewhere. Let's say that the robber is sitting here. Again, I'll use some. Maybe the robber and the cops. So the robber is sitting here. Yeah. And the cops are maybe here. There is one cop here. And one cop here. The big cops should be in red, no? But the rules are, okay, in this particular version of the game, it's a bit funny. One of the cops goes to a helicopter. There is a helicopter hovering around. Okay. So among the two cops, the way they move is that one of them goes onto a helicopter, can look at the whole graph, and then decide to descend on. Because cops are powerful, right? They can use helicopters. For the robber has to go along the edges of the graph. He's driving his motorbike, and he'll zig down. And so the moment a cop goes up, right? And the rule basically is that some cop keeps going up and descending. That's all. And while the cop is up, this guy zigs through, and he can take any path as long as the vertices are unoccupied. Okay. So let's see. If this is the initial position, the robber is here. Maybe I can remove the coloring now that I don't want it anymore. It is on the board. On the board. Because, yeah. So the cops are here and your robber is here. Let's say that one of the cops moves out, and let's say that this guy is off. C1 has gone off. And C1 is going to go up in the air. And the robber moves somewhere, let's say the robber moves to here. And then C1 descends here. Then C2 goes off. And while C2 is busy coming down, the robber, where can the robber go? The robber can go to maybe here. Oh yeah, I'm sorry. Not here because he can go to F. In fact, he can go to C. Remember, as long as there is a path of unoccupied vertices, he can go there. Now let's say that C2 descends here. C1 goes off, and robber will escape to this. Yeah? So you can see that, play the game, try it, and you can see that with two cops, they cannot catch the robber. Okay? That's it. Okay, try it out. Try it out with a few things, you will see. It's a lot of fun to play the game. But what if there were three cops? The three cops with this graph, it's something you can check. Oh, where did I keep this? Keep doing that. I can learn to use this board. Okay, let's see. The three cops. let me start with somewhere. Let's say that I put one cop here, and one cop here. Yeah? And the robber is here. Because there are 3 cops here, this entire path, right? So what they can make sure is that somehow the robber has to go past from here to this component. That's basically it, right? Now if let's say one cop moves out, which one, let's I don't know, maybe this guy, and is going to descend somewhere here. The robber now, the only hope is to keep here. So I don't know, maybe the robber moves to this one. And then that cop which was away will show up here. Then the robber is stuck. And the third cop can simply descend on this and catch it. Right.
Sir,
It's all hooked up appropriately.
at the beginning, the robber is allowed to choose his position.
Initial position, you can choose whatever you like.
Right.
But it's hooked up in such a way that you can see that everywhere there are exactly 3.
Even with that, we can have the robber at L.
That's okay, that's not a problem.
Cop at F. And
Yeah.
the other cop descends at L.
No, initially, right, there are some cop positions and the robber chooses the position accordingly. Right? And let's assume that the graph is non-trivial so that you can always find a place where. Yeah?
Then he's always running.
So that's why he asked and he's right. The robber chooses the initial position so that the game is interesting.
Depending on how dense the graph is, the number of required states of
There we go. Yeah? So depending on how dense the graph is. But is it density that is relevant here?
degree.
Degree is relevant, or what are the kind of graph properties that are relevant here is what you want to think about. The rules of the game are, sorry, I'm trying to skip many things. So the rules of the game are, initially the coppers choose some position. The coppers, there's a right way about it. The cops choose some position. Because of robber, I have to say copper. Yeah? Okay. So the cops choose some positions, and then the robber chooses the position in response. Okay. So this is, robber should be allowed to do that, surely, right? Okay. Now, at any time, one of the cops goes up in the helicopter and chooses a position, descends down. No, so that's what I'm saying. So the robber always gets a chance to run while this guy goes up in the helicopter and comes down. Okay? And there are various ways of formulating, this is one way. You don't know. You don't know. As a robber, you have no idea where the cop is going to descend. But the cop goes up, and there's a certain amount of time, and in between, I run along the edges. And I can choose any path in the graph, as long as there are unoccupied vertices. Right? It should not be blocked by a cop. That's all. I mean, there are very fun versions of the game. Lot more details added, but I'm okay. Anything else? Okay. So, of course, as I said, and as was pointed out, you have chosen a graph which is convenient, right? So, what is convenient about the graph, right? Is it density? Is it diameter? Is it degree? What is the kind of graph parameter that is relevant here, right? And that turns, in fact, the answer is tree decomposability, right? So what do you mean by tree decomposability? I'll define this, but let me show you. Basically, at any point of time, think about what are the places the robber could be, right? Think of the subset of vertices where the robber has a legal chance to be in, right? And take that, try to find as small subsets as possible, and see what is the kind of winning strategy that the cops can have, right? So if you have 3 cops here, I'm saying in this particular graph, 3 cops always have a winning strategy. What do I mean by winning strategy? No matter how the robber is going to move, they can always keep choosing their moves, right? What are the moves available to the cops? Who gets to go up, right? And which vertex to come down on, right? There are 3 cops, one of them goes up and land in some vertex, right? Now, for this particular graph, try to construct a winning strategy for.
So individually it feels like every cop should occupy a color after 3 coloring the.
Thank you. Yeah. So 3. I mean that's precise. Why did I do that 3 coloring? Right. The damn 3 coloring actually gives you a winning strategy. Now, is this all accidental? Right. Of course, when you cook up an example, you can cook up an example with any property that you want. Right. Turns out that the crucial property is just this, that you can actually tree decompose this graph. And I also chose one which looks a little bit like a tree, right? If I were to think of this as one component, this is one component, and this is one component, right? The tree violating parts as components, right? The non-tree parts as little pieces, right? I take those pieces, put together, and I have a tree whose nodes are those little pieces. That's exactly the idea of tree decomposition. I'm sure there are dadas here who know a lot more about tree width than I do. They can correct me. Are there any? I'm sure. Tree width. Come on. Who all know tree width? Algorithms using tree width? 2 hands? Okay. I expected more. So it turns out that this is a very beautiful idea. This idea of graphs that are tree-like, right? So what we are talking about, I think I can get it up. This, I don't know how people work with n colors. One colorability is already hard enough for me. Yeah, okay. So the idea is somehow one of the things you learn when you learn algorithms is that trees are easy, graphs are hard, right? So if graphs are difficult, what do? If you can somehow look for trees in them, right? Look at the wood and you see the trees, right? I love that. Yeah, so you don't see graphs, you should see trees. If you can see trees, you are very happy. So if I can see tree-like graphs, so here is a graph, for instance. I'll come to this graph also. Here is a graph. Let me write it like this. I use a lot of triangles because they're a lot easier. Okay, a graph like this. This doesn't look like anything like a tree at all, right? But it has lots of triangles. Somehow what I can do is to take those triangles as pieces and try to build a tree. So let me again give some names so that A, B, C, D, E, F, G, H. Yeah. So what I do is let me look at this triangle. I'm just going to write it as GHD. What I mean is a set. And I'll have DEH here. No. HIE. EIF. And yeah. Kind of CDE. So what I have done is, I hope it's correct, yeah. ABC is this triangle, and then I take the next triangle BCD and I put an edge there. The 2 triangles share an edge. That's all I'm doing. ABC, BCD, CDE, you can see.
CD is
It's not a triangle, it's a path, okay? But it gives me the path I want, right? To DEH, this triangle, which then takes me to GHD and HIE, and EIF is one that I get. Yeah? So sets of 3 elements. With that, I can get a tree. Now, what is the relationship between the tree and this graph? Okay. So, I am interested in graphs. So, you call a graph tree decomposable. So, I take a graph G and I come up with a tree T, right, such that these are the conditions that I want. Every node of G is present in a piece in T. A piece is what? Some connected component of that graph.
Sir, this is like a dual of a planar graph.
Hey, listen, there is some more going on. Not quite. So, then every edge is every edge UV is a subset of a piece in T. By which I mean that if I have UV as an edge in the original graph, the 2 element set UV is a subset of the set that I have got as a piece. All this can be formalized properly. I'm just trying to give you the idea. And if you have got, let's say there is a path T1 to T3 with T in between, right? If I have a path from some node T1 to T3 in the tree with a node T in between, and now I have a vertex V which belongs to, let me call it VT1. If you take the piece in T1, the set there, and if it's there in the intersection, this implies that V belongs to VT as well. If a vertex is there in this piece and it is reachable in the tree and V is there, then it should be there in every intermediate one as well. Yeah?
So how do you get
There is no?
triangle CDE? How do you construct CD triangle?
No, it's not a triangle. I'm sorry. I'm saying I take the triangles, but I also, I can take any subset of vertices. Right? In this particular case, the path does the job. I just want some way of reaching from one to the other. That's all. Yeah?
Is the path T3 or
Call it, I just called it T, you can call it T. Oh, this should be, then I call this T2. Yeah? T1 to T2, there is a path, and a vertex is there in both ends, then it's there everywhere in between. Yeah? So, such a graph is called tree decomposable, and in this case, you say G is tree decomposable, and the tree width of G is whatever is the max, right, basically the size of the largest piece minus 1. That minus 1, so basically I take the cardinality of the pieces. I have chosen it all to be 3 here, but it can be different subsets. Basically they are subsets of vertices of the graph. So you take the cardinality of each of these and take the maximum. Minus 1 is called the tree width. That's mainly because you want to make sure that a tree is a graph as well, right? And the tree will have some tree width. That should be 1. That's why you. So you want pairs for trees so that it's adjusted so that this happens. That's enough. There is a whole lot of stuff on tree width, all extremely important and interesting, but that's enough for me to state the theorem that I want. Now I'll go back to. Sorry about this back and forth.
Sir,
Which is the one? Yeah.
this need not be a triangle, it can be a quadrilateral as well, right?
Which
This size of largest piece so this
can be anything. So that's why the tree width is something that we don't know what it is, right? In this particular case, tree width is 2. Yeah. Okay. I'll erase this.
effectively a 2, 3.
Effectively a 2. 2.
हाँ.
Yeah. So tree width is 2 in this particular case. Yeah.
So I mean like 2, 3 in the sense of the construction of K trees.
Ah, okay. Yeah. So let me. Here. Okay. So let me skip this. We've already talked about. And so the call strategy can be turned into a tree decomposition. Okay. Now comes the theorem. If you had, when restricted to graphs, a bounded tree width, that means bounded tree width means what? It's if I'm taking a graph which happens to be tree decomposable, and that tree width is something that I fix, right? Yeah.
Sir, I was asking, is this the only way to decompose a graph into a tree? Or
No,
there are
it's not unique. You can have lots of tree decompositions. Tree decomposition is a beautiful thing to explore and do. Look for graphs, and also is there an algorithm to tree decompose a graph? If I tell you it's tree decomposable, give me a procedure for doing it. It's all fun, good algorithms, lot of interesting questions. I want to just move on. Because for me, there is something interesting here. The moment I tell you that a graph is tree-like in this sense, all the following problems are in NC. NC, if you don't know what it is, again, don't worry about it. It's a subclass of polynomial time problems. It's contained in P, and these are what we call parallelizable. But doesn't matter. Vertex cover, feedback vertex set, minimum maximum matching, clique, independent set. 3 dots to say there is more. Partition into triangles, partition into isomorphic subgraphs, partition into Hamiltonian subgraphs, dot 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 dot. If I give you a H and I ask for a subgraph isomorphism into H, graph homomorphism, whole lot of things. Degree contained spanning tree, bounded diameter spanning tree, whole lot of stuff. So suddenly you find that if my input happens to be of a particular kind, all kinds of algorithms, all polynomial time algorithms, parallelizable algorithms come. But people are painfully doing this, trying to come up with an algorithm for each of these, and they were actually writing lots and lots of very nice papers, earning good salary, proving all these theorems. I like to, there's a beautiful song, I don't know if you know this song, from the Ira and George Gershwin songbook. Nice work if you can get it, right? And you can get it if you try, that's what. And then the song ends with saying, if you can get it, who could ask for anything more? I would like to play it on YouTube if you have the time. Yeah? So, tree decompositions are really, if you can get it, nice work. So all these problems share one very nice property. In 1990, Courcelle noticed that all of these problems, with people who are having a good time getting algorithms for, were actually describable in monadic second-order. What is that? It's basically the language of quantifiers that you use when you learn your math. For all x, there exists y, and so on. So that means when you are talking about graphs, when you say for all x, you mean for every vertex x. There exists y, there exists a vertex y. But now, what do you mean second order? You can also write for all big X to mean for every subset of vertices x. There exists y, big Y, which means there is a subset of vertices. So that's all you need to know. So it's exactly the same language with and, or, not, etc. And for all x there exists y. But in addition, you also have quantification over sets of vertices. And that's all. So for all x means universal quantification over this, there exists x means existential quantification over subsets. Again, no, you want to remove all that. For instance, to say that a graph is three-colorable, I just need to write this. I hope you can see it, otherwise you tell me. What do I mean by writing this? There exists are, is it visible or should I use black? Is it okay? Right. Okay. So there exists three sets RGB. What does it mean to color some vertices red? I collect all those vertices, I have a subset, right? There exists a subset which I call R, there exists a subset which I call G, there exists a subset which I call B, such that for all x, for all y, if there is an edge from x to y, between x and y, under a graph, then what do I want to say? Firstly, Rx implies not Bx and not what is that? Gx, yeah, sorry. Just to say it's a coloring, huh? Bx implies not Gx and not Rx, and Gx implies not Rx and not Bx. And then first it's a one of the colors, and Rx, I'm sorry, or Bx or Gx. Okay, that means every vertex is going to get exactly one color. And then what else? Yeah, Rx implies not Ry and all this, not By and this, not Gy and this. Yeah, there are many ways of writing such things. Here is one way of writing it. That's all. Yeah, that's all you need to know about monadic signatology was that you can write such things. That the fact that precolorability I can write like this is something a very routine exercise, right? So the fact that when you've got a tree decomposition, you can make use of that. Yeah, sorry.
So is the number of quantifiers important here?
Yes. So 3 second order quantifiers followed by 2 first order quantifiers. That's something of use. Okay. Let me shut it down. Sorry. Yeah. So, and this is what Courcelle's theorem says. Let phi be a monadic spirotologic formula, anything of this kind that you have given me, and k be a number, then the set of graphs that satisfy T and whose tree width is bounded, where k is some constant, can actually be decided in linear time. And I'm going to give a one slide proof sketch of this. Obviously that's not easy. So first thing is that somebody has told you that its tree width is 2, right? Some bounded number. So compute a tree decomposition of G in time linear in the size of G. I told you, no, this is something you should try. This is Boltlander's, there is a very nice algorithm due to Boltlander. What about K? It's actually some computable function of K. I'm going to hide some detail on that. And now comes this beautiful thing. This is really hard. Now, you gave a formula on a graph. Now, ಸ್ವಲ್ಪ adjust ಮಾಡಿ. Something if you come to Bangalore, you have to learn, right? So, थोड़ा adjust कर लो. Change the formula which was on a graph to a new formula which will work on a tree, right? So that's something you can do. But this is the hard part of Courcelle's theorem. And now comes something that, well, I hope you know what that means. Here's a formula that is true of trees. You can turn that into a tree automaton. What's a tree automaton? It's a finite state automaton that runs not on words whose input is a tree. How does an automaton process a finite tree? Well, one good way for it is to start from the leaves. Starts at the initial state and the leaves, reads the letter, changes state, and at any point of time, if let's say there are 2 children, the transition function tells you that if you are in Q1, Q2, and you read this letter here, this is the new state Q. You keep going up like that, you will arrive at the root in some particular state. If that state is a final state, good state, accept it, otherwise reject. You can do that. And then finally you say that the formula is true in the graph if and only if this particular automaton reaches an accepting state on the tree decomposition on the tree. And this property is linear time checkable. So you do all of these together and therefore you get a linear time algorithm for checking your properties. So I said, okay, this I usually teach in my second logic course in math science, and that step about adjusting the formula takes a couple of lectures. So the details are tricky and hard, but it's a beautiful theorem. In the end, you get a uniform, very, very powerful result. So once you have Courcelle's theorem, you can do a lot better. If a problem can be described in monadic scanner logic and the input has bounded tree width, then there is a parallel algorithm running in time order log n. Not just linear time, but you can bring it to log with parallel polynomial number of processors, or linear number of processors in this case. And if the problem can be described in MSO logic, and it has bounded click width. I haven't told you exactly like tree decomposition, you can do a click decomposition. It's also very nice. And then you can get a polynomial time algorithm. Another theorem says that, okay, forget all this, set quantifiers, you had only first order logic, and if the input was a planar graph, then there is a linear time algorithm for it. Here is one. If the graph has a forbidden minor, if you don't know what that is, don't worry about it. But if you know it's something very nice, that then you can actually get a polynomial time algorithm. So these are what we call metatheorems, because these things have the idea is that logical definability and certain class of graph properties come together to guarantee existence of algorithms of a particular complexity. That's the main takeaway that I want to have. Now the thing is, these are the old results, and the recent results are basically they are of the if-then form, which was your question. The recent results are trying to prove the other way. They are generally hard because you have to prove some lower bounds. So they are not as neat and that I can present, right? But with a lot more tricky stuff, you can actually do the other way as well. And the metatheorems are on space complexity, circuit complexity, for those interested. I'll just mention one. L is the class of what are called log space computations, right? Problem solvable by a Turing machine using only logarithmic amount of space, log space. So Courcelle's theorem, I can actually refine to show that the properties are not just in linear time but in log space. Okay, so that takes more work, and so you get log space algorithms for, you remember all that nonsense that I was talking about, recalculability, perfect matching, reliability, reachability from the source vertex, whole lot of things you get log space algorithms. And log space algorithms are what computer scientists would call efficient algorithms, right? Because your workspaces, I mean, you would like constant space, but you settle for log space. The point is, this is a corollary to this theorem. And as I said not too long ago, each of these would have been, a paper and soda or whatever, right? And you come up with complicated algorithms, right? So logic gives you this ability to give you classes of algorithms, not single algorithms. And there are very interesting things that happen. I should skip this. Yeah. And so here comes the thing somebody was asking about. So Fagin's theorem basically shows, right, that a property is in NP if and only if it is of the form, not just existential second order logic. I chose it in this particular form. 3 set quantifiers followed by 2 universal first order quantifiers. So what about properties where I have got not for all, but for all there exists? What about only 2 set quantifiers and for all, right? Only 1 set quantifier and 3 universal quantifiers. All these are interesting, some are open, some are fixed. There's a lot of very interesting research that's going on. So here is one very nice theorem, maybe I should skip this also. So by now, many of these results have been refined for log space. And for instance, I put there exists one to say that's a set quantifier. If I have a single existential quantifier and then for all sigma, it's in this circuit class called AC0. If I have 2 of them, you get log space. If I put, there exists one sequence of first order quantifiers and then one exchange, I get non-deterministic log space, NP and so on. So my point is that by simply analyzing these very carefully, you can link with different complexity classes. That's the main one. So it shows that somewhere, like she was saying, right, when you are reasoning about algorithms, you are actually reasoning in some logic. With some, and not just some logic, that's the point, you are actually having some particular quantifier alternation in your head, right? And for me, these results dig out exactly the complexity of the logical resources you are using in your reasoning, right? When you formulate certain heuristics and work on certain classifiers. So, and by the way, so I should mention that these kind of results exist for other kind of optimization problems as well. I have not touched any of that. So in conclusion, so this logic algorithms connection is quite insightful, and basically it gives you existence of uniform results on existence of algorithms. And as I said, there are good open questions on, for instance, I said bounded tree width, bounded click width, I mentioned one result, but are there log space algorithms? We don't know any one of them. Almost all the ones we know are polynomial time algorithms. So you've got, somebody talked about dense graphs, classes of nowhere dense graphs, classes of sparse graphs, whole lot of classes of graphs, similar results are being. And then we found the use of tree automata here. What about automata running on graphs and their connection to logic? This was the topic of a talk which Aishwarya was giving this morning in Azimghazi University. So you can talk about graph computations where you actually look at automata that run on graphs and actually get finer clues in these things. Okay, thank you.
Do you have questions? Thank you for the great sales pitch on logic theorem. It is a token of our appreciation.
Oh, thank you.
He did his PhD from Texas A&M, and his research interests lie in theoretical foundations of reinforcement learning. So today he is going to talk to us and give us the basics of RL. So please take it away, Kishan.
Thank you, Aditya, for the nice introduction. So just to add up, like I also did my master's here in EC department, so I'm an kind of an alumni. So this talk will be mostly about like basics of reinforcement learning, and then hopefully, and then I won't be talking about theorems. Hopefully this is interesting for you guys. And then this is a slides adapted from our own like Caltech RL bootcamp we gave. Hopefully I'm audible enough to the last row. Yeah. So the agenda of this talk will be like just to go over what is R. Sorry? Yeah.
You can put the mic a little bit further up.
Yeah. Now I'm audible, I guess.
Better?
Hopefully better. Yeah. So the agenda of this talk will be to go over what is RL, right? Like hopefully you guys are interested in like reinforcement learning and more machine learning related areas. So this will be like one part of the graphs which Professor Ramanujam talked about, but more in the machine learning context, right? And I'll also compare this RL with supervised learning if you have seen if you have taken courses in machine learning, right? And then I'll be just discussing about Markov decision processes in just a couple of slides so that you have like more theoretical intuition of like how grounded RL is. And then I had this demo for like you guys, but I don't think I'll be able to present this. It needs to be on my own laptop because it needs my credential and so on. So right. Before going ahead, I'd like to keep a couple of pointers, right? So this talk will be mostly about like foundational things about reinforcement learning at a high level. So we won't be talking about the state-of-the-art algorithms itself. So So this is a couple of non-exhaustive RL resource you can follow, and then if you want to like deep dive into reinforcement learning as well. So first is the the classic David Silver lectures, which started from the DeepMind, DQN era, and so on. And then there is a local NPTEL lecture, Professor Ravindran from IIT Madras, and then Professor Emma Brunsky from Stanford's lectures as well. And then if you want to get into reinforcement learning and introduction, Sutton and Bartow is a nice book. And then these other three resources are like more depth into reinforcement learning itself. I'll be like showcasing that slide in the end too. Like we can. So what is RL, right? Reinforcement learning is a machine learning approach to solve some tasks by like trial and error methods, just like how you train your dog by some treats and so on. And then deep RL refers to the combination of reinforcement learning with deep learning techniques like neural networks and optimization tools, right? So where is it used, right? RL is used in like games, for example, starting from 2015, the DQN algorithm, which was able to play more Atari games, and then AlphaZero, which was able to play 3 different high-dimensional games like chess, Go, Shogi. And then hopefully you guys are like following chess, which is happening right now, the game 10 of the World Championship. Hopefully Gukesh wins. It's fine, one of the Asians will win. So and then there's more complex games like StarCraft, which DeepMind was able to like play using AlphaStar. Right. And then RL is also used in more complex tasks like robotics, right? This diff is showcasing one of the simulators of robotics, not per se real robotics. In reality, it fails sometimes, right? So let me see if it plays. So it's a very complex task. So since you don't know the terrain itself, the robotics are designed to solve some tasks which you are not seeing in the simulator. The simulator is so simple in the environment space. The environment is so complex. So I can go on showing the failure cases of robots, but I also want to show. Okay, let me see if I can pause this. This is an active area of research, right? Like from top schools like Stanford, MIT, even IISc, right? We want to include local Indian schools too. So anyway, coming back to the use cases of reinforcement learning, right? Reinforcement learning is also used in the recent alignment of large language models. It's one of the blocks of LLMs and not entirely the full pipeline of LLM itself. So this is an example of the older GPTs, right? Like if you give a prompt like what's the purpose of the list C in this code, GPT-3 would like give rubbish answers, and then if you used some human preference kind of labels, if you prefer one over the other answer, like humans would have like ranked the better answer above than the previous one. so that you can use that to fine tune your model, and that's what Instruct GPT is doing. So that's what the underlying notion of GPT-4 is. So this is like a motivation of why you want to study reinforcement learning, right? And then it barely touches the grasp of like reinforcement learning. So current LLMs are using something called RLHF, which is like reinforcement learning from human feedback, which is not the entire like space of reinforcement learning. If you see Andre Karpathy's tweets, you would see like his quotes on like the current LLMs are not using the garbage, are using garbage RLHF or something like that. So anyway, coming back to reinforcement learning, right? Let's go over the basics and terminologies involved in designing the problem in reinforcement learning. So yeah, you might have seen this figure if you have like dealt with reinforcement learning. So this is the start of the figure which you want to get into reinforcement learning, right? So you have an agent, it interacts with the environment, for example, via some actions, and then you get to see some next state or observations and reward how well you are doing in the environment, right? It's not exactly the positive labels, you are also getting negative labels like negative rewards and so on. For an example, like the agent can itself be a neural network interacting with the Atari game, right? Via some like joystick actions, and then you get to see the reward from the scores itself. And then the next state would be the image of the Atari game. Since you don't have access to the dynamics involved, so you get to see these like the screen of the Atari game. And then what's the goal of the agent, right? Just to maximize some kind of objective, which is like cumulative reward, for example. You just sum up all the reward from all the time steps, and then that's the return of your objective. So let's deep dive into like each of these parameters, right? The first one is the states and the actions. What's the state space, right? It's all the possible states which you can like interact in the environment. So it is common to like assume that you are starting with always the same state. For example, Atari game, you're always starting at the same state. Or it can be stochastic as well. If, for example, in robotics, you need not like start in the same state every time. Or the state space can itself be discrete or continuous. It depends on the problem which you want to solve, right? And then there might be terminal states, like you are dying, you are trying to reach a goal or something like that in some tasks. And then there might be like open worlds where you are just given positive rewards every time you fetch something, or so there might not exist a terminal state. So there might exist a terminal state. It depends on the problem again. So the action space is again like what kind of actions you can give the environment as an input so that it evolves into the next state. So here as well, like the action space can be discrete or continuous. And then even the action set can depend on the state space itself. For example, in robotics, you want to take safe actions in particular states, and then otherwise you will encounter very negative reward, and then your robot will die. Hopefully, you'll be getting funding from your department. So, as an example, right, like I'll keep using cardpole as a running example as of now. So the task is very simple. Like you have to balance a pole on your hand, like which you have played in the childhood or something, and then it takes DeepMind or OpenAI kind of like use this task to like benchmark your reinforcement learning algorithms. So in cardpole, the dynamics is very simple. Like it's a 1D line where the cart is moving left or right. So the action space is either left or right, right? And then the state itself is like the position of the cart. For example, so the position of the cart itself, xt, which is like bounded between -5 and 5 on the single line dimension, and then the velocity of the cart itself. And then the other two parameters are corresponding to the pole, right? Like you want to also capture the angular velocity of how fast it falls and so on. And theta t is the angle of the pole itself. Like if it is greater than some degree, you deem that your task is not done. So this is like a simple cardpole example. And then in the Atari game itself, I mean, the current state would be a stack of images, right? And then the image space itself is like, it can take 256 and it's a RGB space, so, I mean, some numbers, right? Again. And then the action space itself is like discrete here, like the joystick actions are discrete. The older analog devices had like more control. So now we can like think of discretizing them. So this was the running example of states and action spaces, right? So let's talk about the environment itself, right? So you typically represent the environment model by a transition distribution. So it typically like stipulates what's your next state probability would be given the current state and action. For example, in the card poll, given the current state, if you take the left action, what's the probability of going into the next state would be, right? And then this is not a single distribution. You have to see carefully that for each state and action, you have a transition function, right? So it's more of a collection of these distributions. And then the transition kernel itself can be deterministic and stochastic. What do you mean by that? In cardpool, since the physics is very simple, given the current state and action, it always sees the next state with fixed probability. So you always see the same next state given the current state and action. And then the robotics, you saw that since the environment is so dynamic, so evolving, your stochastic, I mean, you will see the stochastic transition kernel, right? So yeah, there are other parameters like episode and horizon. So what do you mean by episode, right? Like it's a trajectory of how you sample your current state and action, and then how you evolve in this environment via some actions. And then the horizon t itself is the number of steps in each episode. It can be finite or infinite based on your objective. So there are a couple of different objectives in reinforcement learning. You can think about like infinite discounted value, which is what most of the traditional like famous algorithms use. And then the horizon itself can be stochastic too. Like you can change, you can play with the episode length and so on. As an example, in the card poll situation, the termination criteria is very simple, right? Like if the poll is greater than plus or minus 12 degrees, then you can stop the episode and terminate it. And then the card position itself can't be like going outside the boundary, so you can terminate after it goes away. And we can also limit the episode length. Like if you have solved a task, you don't want it to be like going to infinity. Like you just want to limit your training time. So in another like more real world example, like EV charging, like if you have a couple of customers coming in and then try to charge the car and so on, in a day you can like discretize your time space for 5-minute interval and then see horizon is 288 steps or so on. This is an interesting space because I'm currently working on this at Caltech on like network kind of problems. If you're interested, yeah, please feel free to contact. And then we have a couple of like gym environments created on these kind of power systems, so feel free to take a look at that. So anyway, coming back to reinforcement learning, right? Like the important parameters are coming now, which is called the reward and the return. So what's the reward, right? Like at the correct states and action spaces, ST and AT, you'll get to see some reward. Even this can be stochastic, and then you can involve this in the transition kernel which I have defined. So basically, at the given current state and action, your next state and the reward will be sampled from these two distributions. So right, the return, as we saw, it's a sum of all the rewards which we have seen in our trajectory. So one of the like most used objectives is the discounted cumulative reward, which is like discounted according to your gamma parameter. So here gamma is between 0 and 1. So if you are using gamma to be 1, for example, then you are just summing up your entire like trajectory rewards and then giving priority to each and every reward in the trajectory. if you are using low levels of gamma, then you are giving like more priority to the current reward rather than the future. So it's more myopic to the future. So yeah, this is the discount factor. Typically, you use like values nearer to 1. That's because you want to like see the longer horizon of your problem and then try to solve it like more holistically. And then Fermat's guarantees are usually like provided for strictly less than 1 value because it's more intuitive to see that the horizon the length of your episode somehow depends on your gamma, 1 minus gamma rather. Right. So that's the amount of details I can give as of now. Let's see what's the underlying notion of reward, right? Like you can always translate your goals of your problem into some kind of reward function maximization. Right? Yeah.
Last slide. So you
Uh-huh.
mentioned that it is to the last slide.
Yeah.
Yeah, last slide.
Yeah.
Is it a redundant line? Like, it's obvious that gamma should be less than 1.
No, I mean it can see that if it is 1, then you're just summing up all the reward, and then you have to somehow control your capital T. You should not like make it infinity if you want to solve the problem like any computationally.
So,
Yeah.
can there be any real scenario where gamma will be more than 1?
Oh, it's between always 0 and 1, right? It's a discount factor. So, I mean, if it is more than 1, you're just like giving more incentive to your like reward. Yeah. Yeah.
Okay, I was just thinking in the last line, even if you don't keep, like, is it not obvious? Gamma anyway cannot be greater than 1.
Yeah, gamma cannot be greater than 1. Gamma can be 1, but that's a different problem. So now you have to keep your T finite, and then that's called finite horizon reinforcement learning, and then that's more like complex in some sense. Yeah. Yeah, I can point out that when I come to that slide where I have a policy, I will discuss about the policy space itself. So yes, what's the hypothesis of the reward generation in like different problems, right? For example, in Courcelle, you can always give positive reward for every step you take, and then you end the episode, and then you get 0 rewards. So you have to just maximize the cumulative reward rather. So in Pong, for example, you get to see the points as a score, so you can treat that itself as the reward. It's so simple. Yeah, but in chess, it's more complex, right? You get to see sparse rewards instead. You only get to see +1 when you win. So it's more about like solving this the chess problem like more computationally tactically with graphs, for example. So the other example is like EV charging, right? If you get to see positive rewards if you have charged more number of vehicles, and then if you get to see less number of rewards, like if you have seen less number of user satisfaction per se. Right. Let's talk about other like parameter. Oh, you have a question?
In the last slide, you mentioned EV charging. Can you just talk about what are the problems that we're trying to solve with that?
Right.
Also, I don't understand what is the issue.
Yeah. So in EV charging, the goal, like per se, of the problem is to like maximize the user satisfaction, right? So there are like number of cars coming in, like they want to charge their vehicle, they will like plug in their car, but they're not able to fully charge their vehicle, for example. So you have to, it's a scheduling problem, and then you have to like, try to like charge each and every user's car, and then try to like maximize the user satisfaction. So one of the ways that you can incorporate this feature into the reward itself is like how many cars you have like pushed into the queue, and then like that can be the reward. So this is the underlying problem we are trying to solve. Yeah.
So we're trying to determine what time we need to give to each car.
Right, exactly. Yeah. So for example, if a car has 80% and then that user has some OCD and then plugs in, and then you have to give like less amount of batteries to charge that vehicle, for example. Hopefully no one gets offended if there are some OCD folks here. I myself is OCD, so yeah, a policy is a strategy that an agent kind of uses to decide what action to take for each state, right? So, I mean, when I say this, it's so simple, but it's reinforcement learning is a bigger high-dimensional problem where you have continuous state space. So you have to play this more strategically. On mathematical optimizations is what you want to use in reinforcement learning. So let's talk about policy, right? Like policy can be deterministic. For example, you just map each state to the action, and then simple example is like ping pong, right? Like if you see the ball above the paddle, you just need to move it up. So right, and then a policy can be stochastic itself. For example, you can like to explore an environment, you can deploy a random policy just to like see how it plays, or you can like, use some kind of greedy policy if you have some kind of uncertainty involved, if you want to take actions corresponding to the states. Right. So this was the basic concept overview of reinforcement learning. Right. We have seen stage-based, action-based, episode, reward, and then transition kernel itself, which is, I mean, the key important factor is the return, right? So if you only have this return with your hand and then nothing else in your hand, like for example, you don't need to see the, you don't get to see the transition kernel, then this becomes a reinforcement learning problem. So if you have access to this transition kernel, the next state distribution, so you have the complete information of your system, so now we can like use any kind of mathematical optimization tools to solve this. So that's what the MDP is about. So in the MDP literature, you use any kind of planning algorithms to solve for this return, right? And then if you don't have access to this transition kernel, so you go into the reinforcement learning setting and then try to propose different kind of algorithms, which we won't be talking about. So anyway, right, we saw a couple of examples, right? Like you can define each of these parameters for your problem, I mean specific problem you are trying to solve. In the chess itself, the state space itself is just the board, the 8x8 states of the board, and the action itself can be the piece itself, right? So I mean, I can talk about like different applications, like Pong, for example, and then most recent and then most exciting example is Sony AI's Sophie agent, which is like deep reinforcement learning algorithm, which was able to play a high-dimensional game like Gran Turismo. So where you have almost an F1 car and then different levels of car, and then you have to like take critical decisions at each and every time step, playing, I mean, different players, and then they were able to beat very good professional human players to Gran Turismo. So yes, let's go ahead. I'm not sure like why this picture didn't appear. So anyway, I had a robotics picture, so we have seen a couple of robot examples. Right, RL concepts can be applied to that. So right, RL policies, right? This is more important when you want to implement something. So let's think about policy space a bit. So it's good to like have this kind of distribution of your trajectory itself when you are trying to like pose a maximization problem. So this is like the most technical slide which I have here. So like trajectory tau is like sampled from the current state action and the next state information until some time step period. So now you have this propagation of your transition kernel given the current state and action, and then you are trying to take a particular action from the policy space itself, phi, and then you take the product until the time step t. So this like gives you the distribution of how you want to generate this trajectory. So given this distribution, now it's kind of easy to pose this problem, right? So I mean, taking the expectation according to the trajectory distribution, you want to maximize your return. So you want to maximize according to the policy space. Other parameters are fixed, right? Like you have your probability transition function and then the reward information and so on. So we call this pi star as the goal of the RL agent, right? So and then that's the optimal policy which you want to like reach towards to. Right. In practice, you kind of like replace the policy space, the entire search space of your policy with the neural network, right? And that's the most exciting thing which people want to try and then have tried and succeeded from the eras of DQM and so on. So here, like, we have this neural network parameterized by theta, which is pi theta, the policy parameterized with theta. And then since we are having distributions, we put a softmax on top of this. And then the softmax function itself is just doing the normalization procedure, right, on the neural network parameters. So now the objective turns into finding a particular parameter of your policy space. Right. So now like I can talk about like what's the comparison between reinforcement learning and supervised learning, right? In the machine learning literature, the classical one. So just one slide of review of the supervised learning itself. So you have a function class which you want to fit to the data, and that's the whole paradigm of supervised learning. So what you have access to is the data set. You have the labels xi's and then the the data xi and then the labels yi. It's a sampled IID, and then you want to fit this data set on the top of the function class using some kind of least square regression or something like that. So this is the whole simplest paradigm of supervised learning setting, right? So what's the difference between supervised learning and reinforcement learning? So here you have training labels yi, which are given to you for every data set xi. But here in reinforcement learning, you wouldn't know the optimal actions AT corresponding to the states a priori. Of course, there are other settings like imitation learning, where you have access to the expert actions corresponding to the states, but even there, you wouldn't see the entire state space. And then the data sampling itself, here in supervised learning literature, you generally sample according to IID distribution, but here all your current state and the next state can be highly correlated. And then the feedback itself, right? Like you get to see the label for every data, but here the return RT can be very diverse. Like you can get the same RT for different trajectory, and then you can't decide what trajectory to pick. So, right. So this is more complex in that space. And then there's one setting where I was just mentioning about like reinforcement learning and imitation learning setting, which is more closer to supervised learning. So this is a slide from Professor Amabrensky's course. So where they actually mentioned this thing, right? Like IL plus RL is the supervised learning setting, but in the more like larger space, like your states and action can be continuous. Right. So putting all these things together, we have the mathematical foundations for like something called Markov decision process. So which you define as a tuple of all these parameters, the state space, action space, and then the current reward function, the transition kernel itself, and then the discount factor gamma. So this MDP completely describes the RL environment. What I mean by that is, if you have access to the transition kernel P, now you have access to it, and then you have the optimization problem to solve, which is like finding the good policy. So now you can use your favorite mathematical tool to solve it. And then there are other notions of MDP, right? Like you call the finite MDP when you have access to like the states and action space to be finite, and then if reward function is stochastic itself, then you can include that in the transition kernel, and then you only have one single distribution to care about. So why do we call this Markov decision process, right? The Markov is like more the assumption in the setting itself. So here, if you have seen Markovity, that given the current state and the action, you are making the dependence on the previous states and actions independent for the next state, right? That's the thing which you want to assume. And then this assumption is like more like satisfied in most applications. For example, carpool, right? So given the states and the current action, next state is always deterministic. So it wouldn't depend on the previous states at all. And then the EV charging itself, right? If you have seen the number of cars left at a certain point, you wouldn't care about what happened in the past. The past only affects your learning, right? It doesn't affect the evolution of the system. And then the Atari game as well. If you have seen the previous 4 frames, for example, then the next state would be as an evolution of your current action instead of the entire trajectory. So anyway, this is the Markov. And then there's a good setting of like partial observation. So your agent need not see the entire state space, right? You are only given a partial observation space. For example, in robotics, you are not able to see the entire world of what you live in. So you're only able to see some of the sensors, the informations which you have, which is like the almost imperfect representation of the real world. So yeah. So
in the last slide you mentioned that the future is independent of the past.
Right.
So in the cartoon example, if we take just the state as the position of the pole, so it won't be a Markov process.
Yes, exactly. So
the velocity also.
yeah. So that's why you have to design your state space such that you have the Markovity the principle. Yeah. So most of the folks who design, the design of the reinforcement learning problem itself is a very important problem before using the traditional deep reinforcement learning, which works really well. So if you have designed your problem and then if you deploy your favorite algorithm like PPO, which is used in the industry, for example, even in LLMs, right? Even GPT-4 uses PPO just to replace RL. So in LLMs, it's more complex to design the states itself. You have to take the previous 100 tokens of, for example, if you have more compute, you can look back more into the token space and then design that as a state space. So yeah, that's the most.
You can change the design of your problem to
Right.
convert it into a Markov.
Yeah. Right. Yeah.
Suppose regarding the same statement, suppose we are taking velocity as one parameter,
Right.
and position second parameter and acceleration. So by getting the velocity we are getting position access. So in that sense we are eliminating the past.
Yeah.
In present we have the data. So in that case is it possible that whatever estimation error is there in the past that will propagate to future also, and how will be corrected in case any error is there?
Right. Yeah, that's an interesting question, right? That's the setting which you will be lying here, partial observation. So you are only seeing certain state, not the position, but the velocity and the angular velocity as you mentioned. And then you are still able to go, pose this problem nicely. So here in partial observation, it's still Markov in one sense that it's Markov in the hidden space, which is the entire state space. But not Markov in the observation space. So this is a nice setting if you don't want Markov. But this is a very hard problem to solve. So there aren't many good algorithms to solve this problem. It's all more approximation. But yeah, that's a nice question. Yeah. So if there are no other questions, let me go ahead. Right. What's the goal of this can be thought of as a geek of reinforcement learning, the dynamic programming solution, right? So this is the backbone of most of the reinforcement learning algorithms as well. So I'll just go over it in a couple of slides, right? So you have this notion of something called target state action value function. So you define Q star of SA for a given state and action pairs, what optimal reward which you have seen in the future. So given the entire information of your transition kernel and so on, So you can like always evaluate what this function would be. So here I'm replacing this capital B by infinity. So realize that this is in the infinite MDP setting. So now in this case, gamma can't be actually 1 because you're summing up till infinity. So now this kind of function which gives you the information of your value, being at this current state and taking the action, is what we call as target value function. So why is this useful, right? One is that you can extract the optimal decisions from this function. So you can just take the greedy policy out of this Q star. So for every state, you can extract the maximum action in this Q star and then take that as the optimal action. So this is exactly true from the optimization problem sense itself. And then there's why is it useful, right? Like the other sense is that you can get to solve this Q star in a dynamic sense. So in a recursive sense, rather. So you have this, think of the summation split into the first term and then the rest of the summation. And then the rest of the summation you can think of that as the Q star which is given by an oracle, for example. So that is here, and then you can back up this value to the current state and action and then update your Q star of SA. So this is how you solve the first equation written here. Sorry. So right. Since I don't have the demo like on this laptop, maybe it's good to go over like what's the basic access tools you have to solve reinforcement learning, right? If you haven't seen RL, so this is a nice thing to keep in mind. Yeah.
You can use your laptop for the demo if you want, but this won't be live stream. If you want, you can do that.
Yeah, sure.
Do you have it open?
Right. I can play the demo at the end.
Yeah.
Right. So let's go over how do you codify MDP, right? So OpenAI created this OpenAI gem, for example, which they termed as gem to represent MDP in code. That's the amount of gem nomenclature what they came with. So here, the gem repository would give you a way to implement your environment. You have this reset state, for example, of where your starting state should be, and then the more important function called step itself. So given an action at a current state space, what's your next observation and the reward would be. So this is implemented in the step function, for example. So if you take carpool, you have to define all the physics parameters of your carpool and then try to get the updated observation. So here, this, you have this gym API to interact with, and then what you have implemented in the gym API is the task or at your hand, right? For example, the game scenario or the power grid scenario. So now you want to interact your RL algorithms with the gym API instead of directly with the control task. So you don't have access to the real world data, but you have access to the gym API, which is mimicking what the real world is doing. So now you have different algorithms implemented on different repositories, for example, stable baselines and Ray RLM. These two are at the state-of-the-art baselines. If you want to just play with reinforcement learning, they are mostly written in modular fashion, and then it's not for the research purposes, it's just for getting a feel of what reinforcement learning can do, right? So if you want to modify their code, good luck to you, because it takes a long time to get used to that. But I can point out other repositories, there's something called CleanRL. The focus there is really nice, right? Everything is written in one single file. All the algorithm information, you don't use the other functionalities coming from other places. So, right. a summary of what you have learned, right? So, so we have seen the other basics, like what we picture, which you have seen in most of the reinforcement learning tutorials. An agent is interacting with the environment via some actions, and then you get to see the next state information and the reward, and then how you can like mathematically formulate the environment itself, and then how you can like implement that in the using Gym API, right? And then R solves different problems than supervised learning. So that's the key message in compared to the machine learning scenario. So here are again like a non-exhaustive RL resource if you want to take a picture, or I guess we'll be able to share the slides too after the winter school. So I also wanted to point out like the intern programs at Caltech as well, like it's called Self and Way Fellows, and then most of the deadlines are coming up soon. So if you want to take up the opportunity, and then if you have a bit of a background in like reinforcement learning or general machine learning itself, so you can contact me or like contact my advisors who will be able to like point you to like right resources, and then yeah. Okay, thank you. I had so I finished.
We can do the demo.
Yeah.
Laptop.